So the question is like how to identify a blurred picture and differentiate it from the others. So actually the thing is that if you do you have a specific data set for that?
Not exactly the data set, but some pictures are there. So if you want, I can show you.
Okay, so you can, yeah, actually, yeah, you can show me, but I don't think there are other people. Yeah, so what typically we do is that like let's say like there are like two types of image we need to classify. So what you need to
Okay.
do is that you can just take a collection of non-blurred pictures. Let's say some M, and then you have to take a collection of some M blurred pictures, and you can put labels according to it. Like for the blurred pictures, it will be blurred, and for the non-blurred picture, it should be not blurred. Like
Okay.
zero
So
and one.
creating a data set, like a training set for that.
Yes, yes. And
Okay.
then you need to sort of like train the model
Mm.
which will be so then you need to create a classifier which will be a
Mm.
binary classifier because you have two classes, and using that binary classifier you have to sort of uh, train your deep neural network to classify between the blurred and the non-blurred.
Got it, sir. Got it. Got it. Thank you, sir. Thanks for your advice. I'll be using that. And which classifier would do you feel like works best for this?
Yeah, so you have to use CNN, right? I mean, we have been discussing CNNs in
CNN.
this
Okay, got
lecture
it.
on the past, yeah. So you have
And
to use CNN
send me the,
to.
could you send me the path of this, like, such that like maybe like I have missed some lectures, so I would have the complete repository, and then I'll be able to like check
No,
that.
no, like if you want to run the class lectures, you can access it from the course website. If
Yeah,
you
class lectures are there. I'm looking for these notebooks and all. If
live
it,
sessions, so
yeah,
actually these are shared by the NPTEL people with you. Please check in the announcement section or like somewhere like they must have put the links or your mails actually. So we
got it,
just have to submit the links to them and then they'll
got it. I'll
distribute.
ask.
Yeah.
I'll request. Yeah, thank you. So, what we are going to do today, sir?
I mean, if you're joining this live session for first time, so how this live, give me uh, yeah, how this live session work is that we have to, so we pick a lesson, we sort of pick one topic from this week's content, and we discuss that. And at the end, if the time permits, we sort of run the code associated with this week content
Fine,
and see some results. Yeah.
fine. Thank you, sir. Yeah, please start.
Yeah. So I'll start in just 2 minutes. Just take some water. Let me just start recording and everything, and I'll start in 2 minutes. Yeah. Okay. I'll do this as slide. In last class, we saw that like CNNs are a good way of classifying things, and we saw that like how we can leverage CNNs to do classification of these bigger images, which are not possible with ANNs. So what CNN did is that uh, it sort of found a way to reduce the image size. Uh, if reduce the image size while keeping the while keeping the information content of the image same as the bigger image. And at the end, we got the image to so uh, small that then we can use NN, and we use some fully connected layers to classify that image. So what happens is that what happened is that people started questioning how sort of this CNN works, and why CNN is able to give such good results, because around 2015 CNN was able to surpass uh, classical, I mean, human level classification. I mean, there were some pictures, it was too confusing for humans as well, but CNNs were able to classify them very, um, CNNs were able to classify them very, easily. So, so this lecture we'll be seeing like how can we explain CNNs. So, uh, there were like couple of methods in the literature, like so how can we explain the success of genuine recognizing images. So there were some couple of visualization methods where we just saw something, and we comprehend that, intuitively comprehend that okay, this might be the case, which is triggering this use success classification. So first method is like visualization of intermediate layers. Second is back propagation of the image. Third is visualizing the data gradient for this image reconstruction from the latent space. Fifth is deconvolution, and sixth is class activation maps and some recent methods, which are many. Okay. Sorry, I was on mute. Um, the visualization of the intermediate layer. So what people have done is that they started to look into the intermediate results. So let me just grab a notebook. My skin must not be visible, I guess. Uh, let me computer vision like notes. Yeah. So what happened is that so let's say like we have a intro. Okay, let's say we have like a CNN model. Uh, so we typically represent CNN model like this, and some fully connected layers, and at the end some classification layers, and we have an image. Let's have a cat or something. So we are sort of now interested to know, given this cat image, uh, what triggered in the network? So how this network knows this is a cat? So I mean, this we're sort of answering this question. Okay, so to do that, so some people started with say just look into this intermediate layer. So if you pass a cat, they'll go to the first layer, and it will be there will be some operation, then it will be go to second layer, then third layer, and so on. So what people said is that, so let's say there are like 20 layers. They're like just look at layer 1, 4, 6, 7, like that, like some initial layers, and also look at the last layer, like 18, 19, 20, like that. The reason for people to look into first and last layer is that uh, in the first layers, you can see all these relevant things. So this is the feature map from block 1 up VG16. So these are all the feature maps that you get from the block 1 of VG16. So once you go forward, you can see this is the block 2 of feature map, and it is block 4 of feature map. So as you can see, in the earlier layer, you can clearly see the image of the this bird, and you can see this bird clearly in every feature map. So once you go down the feature map, you can see there is no symbol of this bird in this block 4. So it is not insightful to look into the pictures of the image in layers, which are not in the early state, like 1, 2, or 3. Then what about the last layers? I also talked about it is also crucial to look at the last layers, because if you take the last layer output, you will not be able to see anything. So you'll not be able to find bird in it. But what you'll able to find is that, like, let's say you pass 1,000 images and you get 1,000. Let's say this layer be Z, okay, and you get 1,000 Z. Okay, so if you plot these Z's, so initial layers will give you the representation of the original image. That means like it will give you just if you see here, it will give you the same image, like uh, serpent, like background is blurred, and this is the, I mean, this contrast between background and the subject. So more visual representation of the this bird. But when you go further down the line, you'll get more visually non-appealing images. But when you plot that, then you can see the more you go deeper inside the network, you'll find things which are relevant to a class. So if you plot this Z, okay, what you will do, what you will get, you'll get some point concentrating around some area, and some other point getting concentrated around some other area, and some other point getting concentrated around some other area. So what you did, like you just took 1,000 images and then you just plotted the second last layer of these 1,000 images, and you get this cute, like you get this different clusters that are around across this plane, and you can clearly say that the image, when you pass it in the network in the initial stage, it is very visually appealing, and it is very visually clear that this is the image, and that sort of gives you the structural features of the image. But when you go down the lane, you cannot recognize the image, but towards the end, it will highlight those features which are responsible for classification. So you will be getting features which can be distinctly identified as different clusters if you plot it. So this is the way we sort of know that image is getting passed to the further layers, while the initial layers give us the structural features, and the later layer give us the features which are responsible for classification. So this is one of the techniques to discover about this uh, discovering about the reason behind how why CNN are successful. So if you have any questions, I'm pausing for 2 minutes. You can ask now. Okay, so we'll start the next section. Next way of interpreting our CNN, that is back propagation to the image. So the question is, people that ask is that, can we find an image that maximizes the hub class score? So let me go to the notebook. I'll write here back propagation to the image. Okay. So uh, so let's say uh, you have cats. Try cat, and like you have say, let's say 10,000 cats, and let's say you have 10,000 dogs as well. Okay, that's just a dog. This is cat. This is dog. Okay, so there are 10,000 dogs as well. So, and this is a neural network. This is a CNN that is classifying between cat and dog. Okay, so these are the input. The input is passed to the CNN, and in the end layer, it is classifying between cat versus dog. Is this setting clear, like what I'm trying to do here? Okay. So, so the question is that once this trend image is given, once this trend image is given, is it possible to, once this trend image is given, is this possible to, so once this trend model is given, is this possible to find, what is the knowledge of CNN about cat? That means, so you can ask that, okay, so you're saying this is a trend CNN and this has all the knowledge, entire knowledge of cat and dog. I mean, it knows which is one is a cat, it knows which one is a dog. So, uh, is it possible if I just ask this network, draw me a cat, will that be able to draw me? Or, in other words, is it possible to, tell us what do you think when I say cat, or what is the image of cat in your mind, in the model's mind? Or, in other words, we can ask, so what is the average cat in your mind? So you have seen 10,000 cats as a model when you are getting trained. You have seen 10,000 cats. What is the overall cat picture in your mind, or you can say average cat picture in your mind? So this is like a question, and the question, answer to the question, can it do that? Is yes, it can give us the average view of cat while when we ask about when a model is trained on cats and dogs. So starting with that, so there is an algorithm to achieve that. So first thing is, let me answer now. Yeah, this is the algorithm. So what you will do is that we'll first input a blank image. So what do you mean a blank image? It can either be black or gray or white, like just a plain sheet of image. Okay? All the pixel is 0 or something like that. Okay. So you take an image and let's just name it as X. Okay. And you take an image X, you passed it to the CNN. Okay. And you got an output YX. Okay. And let's just say the CNN is Y, and we got an output YX. Then we need to set the gradient of the score vector to be this, then to backprop to the image. So what you do is that, so when you pass the black image, you'll get some values, some values y1 and y2. Okay, as an output, because this is a binary classification problem, we'll get a score for cat and we'll get a score for dog. Okay, but since you want to get the clear uh, image of a cat, since you want to know what's an image of a cat in the model's mind, what you'll do is that you'll put, for the actual output, you'll put cat as 1 and dog as 0. This is a y hat. Okay, this is a y hat, and now what you will do, you will back propagate. So this is the predicted y. Okay, and so you want this output. So what you want, you want that, you want the mental memory of this model which represent a cat, and once you do that, you sort of so for that, you just pass this image to the CNN with the hope that it will it will, like, come as a cat. But since it is not cat, we need to compare these two and take a loss. So y minus y hat and L2 loss. When I took this loss, this is, let's say, L, and then now with this L, we now need to backpropagate. Okay, we need to backpropagate. Since the weights in the CNN model is trend, we will not change them. So what will we change? We will change X. Okay. So if you look carefully, it is like find me the X which will minimize this loss. Okay. It's like find me a X which will minimize this loss. Okay. So since we have to find this loss, or you can say maximize the existence of a cat. Since when we do this sort of so when you do find this gradient, so minimizing the loss, like what we need to do is that dl by dx, which is saying gradient of the loss with respect to x. When you find that, we can update the image. So image new equals to image plus delta l gradient of l with respect to x. Okay, and so we did that. Then we'll again go to the step 2, where we'll again pass this uh, image to the uh, we'll again pass this image to the network, and we'll find some score. Then we'll update the image. At last, once the image is updated multiple times, it will be able to you'll be able to see the image of the cat that the model has in his mind. So once we did that, this is sort of the uh, image uh, uh, that the model have about different things. So this is this slide. This is the image of a washing machine. This is the image of computer keyboard, and this is the image of Kit Fox. This is the image of a goose. This is the image of an ostrich, and this is the image of a lemonade. So if you see here in the washing machine, here is a washing machine, here is a machine, here is a machine. So it's not like that. It has only remembered washing machine as a defined object, but it is remembering all the assessments that it has seen in its entire lifetime. If you see ostrich, here is ostrich, here is ostrich as well. So, and in the lemonades, here is you can see a wheel, and here is doors, and here is this front cabinet and everything. So what it is doing is that it's sort of trying to average out all the images that it has seen in its entire life. So back propagation to the image uh, got us to like find the um, uh, average value of an object or a class in the model's mind. If you have any question about this, you can ask. I'll be here for like 1 or 2 minutes more. Yeah, I got a question like up until when we should keep on updating X? Good question. It's like when you train a neural network, it's basically like it's not like that we will train the neural network till this point. We train the neural network uh, till the air um, stops to decrease more, or like the decrease in the error sort of becomes stagnant, and there is no significant decrease in the error. Similarly, we will stop updating the image once we don't see much change between two updates. Like if the value of update drops, then we can comprehend that the image that we have now is sort of a final image, and we're not seeing much difference in each update. So we'll stop there, and we'll declare that as a average image to us. Yeah. Okay. Okay. Then image reconstruction from the latent space. Um, so the question is like, given a CNN code, is it possible to reconstruct the original image? The answer is yes. So remember, we are learning this in the context of this explaining the results of CNN in terms of I mean how why this CNN is sort of performing better in terms of the results. So we're saying that if CNN is so much able to do so many things, one second. Okay. So like we say that since CNN is able to classify so many things together, um, then if I just put a pin on on an intermediate layer and try the and say the network to reconstruct the original image from it, it should be able to do, because since CNN is performing better, it should be learning something through its intermediate layer. And if I if I like uh, uh, find if I just give the value of an intermediate layer, the uh, uh, the network should be able to predict the original image out of it. So so, so what I'm saying is that what I'm saying is that what I'm saying is that like let's say this is CNN. If I want to take the value of network from this point and try to reconstruct image, this is image and this image cap, will that be possible or not? So the answer to the question lies in this optimization problem. So the optimization problem, so answer is yes. So the optimization problems uh, tells that if I want to reconstruct an image, that image, the reconstructed image sources code should be uh, similar to the given code. That means, so it is the image, and if you pass the CNN and you get a code C here, and from C you reconstructed this ideas. That means it is saying the code of this ideas, let's say C dash, C hat, should be similar to C. That makes sense, because since we are like reconstructing the image, the image should look like the original image. That's why the intermediate output often CNN when the original image is passed should be equal to the intermediate output of the CNN when the reconstructed image should be is passed. So this is the condition number one for creating the reconstruction of an image uh, from the Latin code. Then coming to the condition number two. Condition number two is it should look natural. It's not like that we are creating an image which look like rubbish, but its code is similar to the original code. Let's think about the the optimization function that is written. Okay. Um, let's say I want to find. So let's say my image is X, and I wish to find the reconstructed image that is X star. Okay. And in my network, if I pass X through CNN, the intermediate output is given by phi of X. I mean, this is equal to C. Okay. So if we look at this optimization function, it says that the image code should look similar to the given code. That means give me X dash, give me X that X star, such that the condition number one is that intermediate code should be same. That means the difference between intermediate code should be less. That means the difference between intermediate codes of original and the reconstructed sample must be minimized. I mean, this is the difference between the original and the intermediate code. We want to minimize this. Okay, I can say argmin. Let me just erase this. Argmin of this, and find X star that belongs to the real number of say height of the image, width of the image, depth of the image. Okay, so this will give me the X star. So it's like we're sort of trying to find the X star or I hat here, where the minimization function is like this, and is the condition number one, that the image code is similar to the given code. Second is it's look natural. So to maintain the naturalness of the image, what we want to do is that we don't want the image to blow away. We don't want the render the image to blow away. So along with minimizing this distance, we also minimize the L2 norm of the image. And as you can remember, this is uh, This is the regularization term, and we just denoted here Rx, and lambda is some Lagrange multiplier, or you can say constant, that keeps this x within a certain bound, and it did not allow the x to explode. So this is the overall optimization problem. So if yeah, you should know that in an optimization problem, the things which is getting minimized or reduced should be put in the loss. So what we do in ML is that we minimize the loss. The back propagation algorithm minimizes the loss. So since we're having this term as a minimization, this is with the loss. Once you put this thing into loss, it will be able to we'll be able to get the corresponding x or corresponding reconstruction of the original input, which minimizes loss. Okay, and so by doing that, since this is the original image, we got different reconstruction of the same image. Why different? Because we started with different x. So what we do is that we'll take a new x, we'll take a new x, okay, and we'll take a new let's say x1, and we'll pass to CNN. This will give us some value, okay, some value that is phi of x1, phi of x1. But the actual value is phi of x, and this is our loss. Once you have loss, you can find gradient of loss with respect to x. And once you find that, we can update x2 equals to x1 plus some alpha times gradient of loss with respect to x. Then we will get x2. We'll do the same thing with x2 and pass it and get phi x2, and then subtract it from phi x, and so on. And we'll similarly we'll do that till we get a point where the image is not more changing. Then you can assign that this image is the reconstructed version of the original image. And there are some more pictures uh, where we reconstructed the image from the latent space, like this fruit getting reconstructed, top getting reconstructed, bird getting reconstructed, and so on. So this was the end of image reconstruction from the latent space. If you have any doubt, you can ask me now about this technique. I got a question, like in what fields this reconstruction of image can be applied? So a reconstruction in general can be applied to many things, such as denoising, anomaly detection, and like just restoring images, or recreating color image from the black and white, or even or just making sure the image is of high quality. But uh, here, what we're leveraging reconstruction is for that we're sort of trying to see if the model has learned properly or not. If the model is like, what it is learning is appropriate, and using this learning, it is able to predict us good output, good classification results. Uh, so now we are now in this study we are using reconstruction to see if what we trained the model for. Uh, we're seeing if what we have trained the model for is working or not. Like we trained the model for, let's say, cats versus dog classification. How is this model is modeling this, or does the model have a good understanding of the classes cat versus dog? So this is the application that we're doing here for the reconstruction. Okay. Then we'll be discussing the class activation maps. So class activation map says that, um, can we know what a network was looking at while predicting a class? It's like to see. Okay, so you say this image is a cat or this image is a dog. So can you point me in the image where you sort of looked at before saying that this is a cat or a dog? Okay, so it's like looking at um, it's like looking at what portion of the image is getting looked at before saying that this is the cat. So for that, what we do is that for the class activation map, we sort of create these maps and see where it is looking at in the each layer. Then we find a linear combination of that to uh, the person get the person of the image where the model is looking at before making classification. So you get the idea, right? Like you just look at each layer where it is looking, and then you combine that to get a place where it is looking in the image. So, so this is like this clean activation class activation map is a linear combination of all the activation maps that you get in the intermediate layer. So, if we see some results, so this is a breed is a like breed of dog. It is getting a class activation map from the face, because face is something that differs. So you can see there is three images of the dog of same breed. Okay, like this breed. But for the model to classify this as this class, it must know it is a dog. Secondly, it must know what is the breed. So if you see these three images, what's common in them? This middle image do not have the body of the dog that other two dogs have. So so you can see clearly in the class activation map, since the class activation map shows which portion of the image is responsible for making this class responsible for for prediction of the network of this class. So uh, it should tell the network should tell us something which is there in all the images of this class. So if you see here, all means three images. So if you see, if in the first image it is looking at the first image, if it were looking at the entire body of the dog, then that is an error, because in the second image there is no body. So the class characteristic maps uh, points at that position of the image where it is distinguishable from all the other images, and it is present in all the images of that class, which is the face. So we can clearly see that to classify this dog as this class, it is looking at the face of the dog before making a prediction. Okay. Similarly, for the barbell, in the second three images, there is an image of barbell. So if you see, there are three different men holding the barbell in three different positions. One is underneath, one is bench press, and one is doing squats. Since this CNN is generalizing across different images, uh, we can clearly see that we can clearly say that the uh, class activation maps only activate the region where barbell is present. It is not even looking at the person that is there. So if you see in three images, the red area or the blue area are the somewhere where the barbell is present. The distance of the network saying that there is a barbell only depend on the barbell. So if you pass any other thing that is doesn't look like barbell, it will not flag it as black barbell. Okay. So with this, there are some pros and cons of CAM. So pros is that this is a self-supervision based uh, method where levels are not needed. And the cons is that it is not suitable for complex CV tasks such as image captioning or visual question answering. So, and second thing is that interpretability and accuracy are two contradicting roles. If you make the model more interpretable, or in a way like you make the model such a way that you can, like comprehend how this decision is made, then there will be a loss of accuracy for that model. So we need to retrain the model to explain the result of that model. So more you make it explainable, more the accuracy drops. So it is very hard to get an explanation for a prediction and get good prediction at the same time. So this is all the theory that we will cover today. Let me see where. Yeah, this is all the theory that we'll be covering today. And so there are supposed to be a coding session for like 30 minutes or 45 minutes after this. So what I do is that I teach for like 1 hour, then take a 5 to 10 minutes break, like for the water and like bathroom, and then I continue for coding for like. So I guess we have 50 minutes left now. I can take a break and then we can continue for the coding, which is generally runs for like 30 to 45 minutes. But unfortunately, like there is a huge thunderstorm coming in my area, so that's why I will not be able to. I'll not be able to record and being or be live for the next couple of hours. Uh, Hopefully, this thunderstorm is stops, and so what I'll do is that so since this is the case, we have done like 1 hour of theory now. So what I can do is that while uploading this video, I will attach a 30 to 40 minutes of coding session as well. So in the chat window, I'll give you the link for the code that I'll be running later when I record the video. What you do is that you just go through these notebooks if you find it handy. And these all notebooks are hosted in the Colab. You can actually access the Colab uh, uh, directly for free and run your models there and run your algorithms there. It is free GPU, everyone can use it, and please use it and run this code. So what I'll do is that I'll stop the session for today now. I will record a session with by running the code and explaining some details of the code, and I'll upload the joint lecture in the YouTube, so that you can find the uh, complete session in the YouTube if you follow me on the YouTube. Okay. So if you have any questions, you can ask now. Then we'll close the session. Okay, great. So there is no questions, but yeah. So every week, I guess you'll be provided with a feedback form. Please feel free to give a valuable feedback about this live session. We'll meet next week around same time. Till then, bye bye. Good night.
Yeah, so this is yeah, so as requested, I will start explaining the code part of the week 6 now. So be with me while I run some of these codes in Colab. Yep. So what you have to do is that if you don't have the link for this GitHub repo, you can look it up in the discussion section and put a question. I will put the link there. But yeah, this link should be shared with everyone who is taking this course, so that you can run the code by yourself on your side. So this is the week 6 code that is from lecture 1, explaining CNN visualization method. So what you have to do is that you have to go to this link, then open the Colab notebook. By just hit here, it will open. And then what you have to do is that you have to connect your notebook to the GPU. So it kind of takes some time to connect. So we'll just wait for some time and see if it is connected to the GPU. Yeah, so you should choose the T4 GPU and save it. Hit save. So you'll connect again and it will be connected to the GPU. Okay, great. It is connected. So what you're doing in this code is that we're sort of visualizing the filters and the kernels of the first layer. Um, so what filters are, if we say, like as we discussed, so there is an NSL image in the input layer, and we're sort of trying to put filters and convolve around the image to get a filtered version of the image. So if we put a filter, so filters at the parameters, and we learn them with time, and at the end of the training, if we have a filter, we can use that to see how the filter is learned. Okay, so at the end of the training, given an image, you put the trend filter and convolve around the image to get the next layer's representation. So that's the idea behind filters. So what you do is that you take so there's a library that's called Torch Vision. So Torch Vision is a library that sort of creates sort of have these models from have these models from all the good computer vision problems. And so that's why, like, when you yeah, like, I mean, it's the library of all the computer vision models, and all are pre-trained with ImageNet. So when you're trying to do a task that involves uh, any sort of image recognition or any sort of image related task, it's easier for you to use Torch Vision to just load a model from it. Everything will be pre-trained, so you don't have to worry about the weights and the training. So what we have done here is that we took the Torch Vision library, and from the models part, we imported the models as models, and we imported the torch as well. So how to load a pre-trained model? Just take models dot Vresnet 50, and in this case, Vresnet 50 is a pre-trained model, and we're using that pre-trained model to like sort of uh, visualizing the intermediate layer and see what is happening in the intermediate layer. So what do you need to do? What do we need to do is that we just need to do models.Vresnet 50. So it will load the Vresnet 50 model, and then you put pre-trained equals true, which will make sure that we load the weights as well along with the model. So if you just load the model, it will just load the random weights associated with it. But when you do pre-trained equals true, it will load the trained weights that was trained with ImageNet. Of course, the syntax now has changed. Instead of pre-trained dot equals true, you now have to put the specific weight that you need to load. Like if it is ImageNet, so you need to put the ImageNet weight. There are like 2-3 versions of ImageNet weights. You can put the default weights, which is the ImageNet. You can put the other weights, which is trained with other data sets, and so on. So basically, like, you just need we're just loading the trained model, and before evaluating, and since models by default stay in the train mode where the gradients are not frozen, so you have to put it in the evaluation mode where the model will only be um, frozen. It will only be used for the evaluation, not prediction, not for training. Okay, so we'll run this cell and see what is happening. Yeah, you just have to hit run anyway. Great. So it is if you can see, it has downloaded the yeah, so as I was saying, you can see the parameter pre-trained is deprecated since 0.13 and may be removed in the subsequent in the future. Please use weights instead. As I was saying, if you put weights equals and the weights we're trying to load, you will get it. Okay, great. So there is that. And the second thing is that the downloading, we downloaded the Vresnet 50 model, and it is around 100 MB, and we downloaded and put it in the eval mode, and you can see the architecture here. Without writing a single line of code, you can download the model. You can download the pre-trained weights. You can get a fully trained models without a single line of code. Yeah, of course there is a single line of code, but it's not much. You can get everything for free, and like everything for like pre-made, and it's just you just have to use it. Okay, so we have the model now. Now what we need is an image, and we'll see how we can transform this image to put it inside the Torch Vision model to predict and see the feature map. Okay, so we imported the transforms from the cross-vision, and also the URL lib. So URL lib help us to retrieve certain things like from the net, like this image. So what we do is that we took this image and we opened this image and we printed this here. We're just printing this image, okay? So here's a crow, the two bird fighting or something playing. So it's an image we'll work with. Then comes to the transformation. So certain models in ML requires you to have the image in certain shape. So it will not affect the content of the image if the image is in the shape of let's say 400 cross 400. But the model wants the input image to be 224 to 224. Then we need to resize it. It's not like that we're sort of chopping down, we're not cropping it. The cropping it would be like chopping down some pixels around the image from all four sides. But what we're doing is that what we're doing here is that we're sort of resizing it. We're sort of keeping the entire image without affecting the size or affecting the information that we're having. Um, give me a second. The sort of give me 1 second. Um, okay, so I'm not able to see for how many time this meeting has been going on, but okay, that doesn't matter. What I was trying to say is that so we need to transform our image into certain size, okay? So what we do is that we imported this transform function from the TOS vision, and what we can do is that we can sort of take this transform and we can compose a number of things that will be applied to the image. So first of them is resize, where we resize the image to 224 cross 224 pixels. So it will just squeeze it without losing anything, without cropping down anything. Okay. Then is the to tensor, which will convert it to torch tensor, and it is like helpful for us because we're working with PyTorch and everything need to be in PyTorch tensor to be processed by a PyTorch model. Okay, great. And when the ImageNet more ImageNet dataset is used to train this model of Western 50. What they did is that they normalized the image. Okay, before training, they normalize the image and then train the Western 50. So when working with another image from the cloud, from the internet, and we're sort of making the prediction now, we're not training now, even though to get, and as all the weights are synced and all the weights are trained in such a way that it will cater to the normalized image very efficiently. So it's the fundamental things to do is that we need to normalize the image with the mean of uh, ImageNet and the standard deviation of the ImageNet to make it normalize as well. So what we need to do is that we sort of need to transform this image to this to all these things and then start playing around with it. So we do the transformation and we apply the transformation to the image. That will be like transform then image, and we need to add one extra dimension to the image. So because like when the image is processed by the PyTorch models, it expects it to be in the shape of like batch size, then channels, then height, and then width. So here we have only height and width and channel. So what we have to do is that we have to unsqueeze it to make it a one batch size image. Like it will be like 1, 3, 224, and 224. Great. So we'll just run it. And the name transform is not defined. Okay, I haven't run this cell. I just need to run this cell. Great. I ran this cell. I need to hit the transform. Yep. Okay, so now let's modify the model to retrain the output of each layer. We'll define a forward hook for each layer and store the output. So what are you doing here? What we're doing here is sort of that we're sort of give me a second. Yeah, so what we'll do is that we'll define a hook now. So what it will do is that it will what it will do is that it will bring so it will take the output from the each intermediate layer and we'll define a forward hook. So what we'll do is that whenever it sees an output in that layer, it will just store it. And later, what we can do is that we can take this output from this hook and visualize it and see how it looks like. Okay, so how do we define it is that we define the hook as a function where the model will be so it will be automatically taking the model, the module, the input and the output. Okay, great. And what we need is that we need to maintain a list of outputs and we just need to append the output in the list. So what it is like that so what it is that like what we're doing is that we're maintaining a list, and whenever we see output after each layer, we're sort of appending the output to the list. Like if you just query the list after the end of this operation, you can find the first element corresponds to the output of the first layer, and the second element corresponds to the output of the second layer, and so on. Okay, great. So what you do is that now we attach this hook to our network. So it's like for layer in model.children, attach a hook to the layer. that will be like layer dot register forward hook, which will just so it will just register the forward hook, and we pass the hook. So for each children of the model, that's like from each layer of the model, we're registering this hook function. And since the models layer works in like that, like it have a, the models layer will be a will again a model, and it has the input and it has output. So these three things will be automatically passed to the hook, and the output will be stored in the output list. Okay, so let me just run this code real quick. Yeah, it's run. Up now we can input our image to the model, and it will store the output of each layer in the outputs list. So this list will be now, so if I just print it, print outputs, it will be an empty list, you can see. Great. And now what we'll do is that I forward pass the image. So when I forward pass the image, it will take the image and it will pass it to the each and every layer of the model, and it will give the final output to me. But if I need the intermediate output, I have attached the hook to each layer. Then what it will do is that it will just try to save each and every layer's output in this outputs list. Great. So what you do is that now we passed the model to the we passed the image to the model. Now I think it's a good time to see the um, output. Um, uh, I'll just print outputs. So I think you will see a list. Yep, it's not very intuitive to see it in as a print statement, but what we'll do is that we'll just use it to, so I'll just cut it, because, and you can see it's still there. It's a list, the list is now filled. I'll just, yeah, I'll just chop it off, and I'll also delete this cell as well. We'll just see the code to visualize this. Okay, so what we're doing is that we're taking only the first layer output, because we have a lot of filters in each layers, and each layers will capture something different. Okay, so uh so what we're doing here now is that so let's say we have 10 filters in the first layer, it will give us 10 outputs. Okay, if you have like 20 filters in the second layer, it will give us 20 2D outputs. Okay, so now we'll see the output of the first layer. So it's like we take the outputs, we take the first element of the output, which is the output of the first layer. And what you do is that so since this will be in tensor, torch tensor, what I need to do is that when it will have a grad function associated with it, and also the GPUs associated with it. So what we need to do is that we need to detach them and convert it into numpy to be printed as image by the matplotlib library. Okay, so we did that. We detach that and put it in the numpy folder, and then we print the first layer outputs. That is yeah, so it's the first layer output, and we just printed the stuff. For visualization, we'll just look at output of the first filter, and yeah, so there's like 9 images, and we sort of uploaded from 1 to 10, and subplot of 3 and we sort of took the first layer output and printed these images. And let me just run it, and is just sort of dealing with how to plot multiple images. We can just plt dot axis equals to off. Axis off. It It will show us the distinct images without the labels. Good. Let me see, try like to do the second layer output. What is happening? I don't think it will be so yeah. So these are the second layer output of size 164, 112, and 112. Let me go and print the third layer output. Yep, great. As you can see, what I can do is that I can put 0 here and copy this code, run this code and copy this code for layer 2, and as you can see, it's getting more complex and complex for the deeper layers and making it more difficult to recognize it. So we can say that the initial layers sort of learn the basic shapes, and the later layers learn the much more complex shapes while training SCNN. Great. And so this ends like the what we have here in Colab as a part of the coding portion of the lecture. But the thing is that you need to design you need to design, what you can do is that you can just go around and see load some different model maybe here. So instead of loading ResNet 50, you can load VGG16 or InceptionNet, GoogleNet, ResNet 32, ResNet 18, 100, 150. You can load these models. It's very easy. It's free. It's fast. So the GPU is free. The models are free. The weights are free. You just need to load it, and you just need to see what is the representation of images in the intermediate layer of these models. You can do a comparative study as well, but yeah, that is not necessary. But you can say like which intermediate layer learn the image better. Okay. Okay, great. And moving forward with the coding part, so you can do that, and you can get the output, and you can see the results. So moving forward with the coding part, let me say, like, do we have any much, or do we have more notebooks that need to be that is there? I can go back. I'm not sure why it is taking so long to go back. It should be leaving this idea. Yes. Okay. So here's a bunch of notebooks that we have with here. So that was lecture 1. We have code in lecture 3, slide 3 as well. Let me see, explaining CNNs and class attribution map methods. So it's the CMap code. Let me see like what it consists of. Okay, so transform the image code. Yeah, great. But this seems a little much for us to cover today, but I can briefly say what it is. So you can say all these imports are there, that's fine. And if you see, is the same as we did now. It's just loading the ResNet 50 model, and then like we're sort of storing the feature map of each layer by using this hook function, and we're sort of doing this transformation, which is exactly the same that we discussed now: resizing, tensoring, and normalizing. Loading a sample image is exactly the same. Then loading the model, unsqueezing the image by accommodating the batch size, then putting the model in the eval mode and getting the features and getting the output is also the same. But what happens here is that this part is sort of new, where they're doing the predictions and looking into the weights of the model and trying to figure out how these weights and how these weights are put together work to like activate the image and certain part of the image. It's not like that when the model is making a prediction. It's not like that. It's sort of looking at the entire image before making a prediction. So what it does is that it look at a certain portion of it to make a prediction. So since it is a tiger, it should be looking into the tiger's body, not elsewhere, not anywhere else. So what we saw here now is that it's looking at the tiger's face, his body, and the texture of his body to make a prediction. So this says that this model is well trained and it is looking at the right place to make before making a prediction. So here's a bunch of other things for you to see. You can easily run this code and see the outputs, and this is the first out, like this is the final output of like where the tiger may be and where the image is sort of looking before making the tiger's prediction. This is like sort of a segmentation more segmentation version of the same thing that we are seeing here. Okay, great. I think we can end the session for today now, and we will meet next week in the week 7. Till then, bye bye, good night. Thanks for joining and doing this meeting with me. Thank you.